Also wir haben heute sehr viel über Visionen, zukünftige Konzepte, Technologien.
We talked about future visions, future concepts. We talked about AI. We talked about neural networks. My presentation and Mr. Schramm's presentation will be more down to earth. We're talking about a specific subject. We are talking about an ECU, which is being implemented in our factory in Rouen. It's a multi-core embedded operating system for our function development on an ADAS ECU, and we also use the system. Well, where do we come from? What is our vision, and why do we look into this subject? Well, Autoliv is a company which has a vision, and our vision is to save lives in road traffic. And we actually have lots of studies going on, and in the field we save over 30,000 lives per year. And we protect a factor of 10 of these lives from severe accidents. And of course, it is our vision to even improve this situation.
Unsere Produktionsprozesse sind so strukturiert, dass wir
Our production processes are structured such that we produce our products according to one approved standard on a worldwide basis. So we want to be transparent and agile. How does this manifest itself in the project that I'm responsible for this OEM? I can give you a magnitude. In 2017 specifically, we developed 16 software supplies for this OEM, and we also got approval for use on roads. And actually, this means a 3 to 4 weekly interval in which we finalize software development with the verification and approval for road release. And of course, you can only do that if you work based on stable components, hardware and software. And I'm focusing on ETAS OS and the AUTOSAR stack, because this is really the basis for us in order to get road release.
Unser Anspruch ist in diesem Bereich Zero Defects.
So it is our aim to produce zero defects. For all those of you who work in series production, you know that it is a challenge because you're not the only one who influences it, but also your suppliers. So it's still our aim to make sure that this happens. And we are trying to identify everything as early as possible and exclude any errors for our OEMs. And we want to be structured such that every product that we produce can be produced around the world in our factories according to the same standards. And just like ETAS or Bosch, who have given presentations here today, we would like to be innovation leaders.
Was ist unsere Vision? Ich habe am Anfang von meiner kurzen Einführung erwähnt, dass wir aktuell 30.
Now, right at the beginning of my presentation, I mentioned that at the moment we save 30,000 lives per year. And of course, this is not just some figure, but this is actually knowledge that we have, and we can also prove that we have that in our databases. And it is now our aim to increase this by a factor of 5. Now, what is the vision that drives this? And how can you do this with more than just passive systems, belt systems, airbags, things like that? So you've got to look ahead, and this means that you've got to go into active safety systems, accident prediction, accident prevention, autonomous driving, free space detection, things like that. So how do we do that? Autoliv, as I said, is something that most of you will know from passive safety systems, airbags, but we've now been looking into a number of other technologies, radar technologies, blind spot detection, front radars, front corner radars, cameras, mono stereo cameras, positioning and horizon systems, software features, function development. That's an important driver for us. Now, if you think in AUTOSAR nomenclature, its functions below the RTE layer. We look into both active and passive safety. ADAS ECU is one thing that I mentioned earlier on. It's the brain in the vehicle in order to provide for sensor integration, data fusion, and implementation of function algorithms. We look into night vision systems, night vision assist. Also, steering wheels are in our portfolio. And, you know, in the meantime, we've also started to look into braking systems, brake systems. And as far as I'm concerned, I am a project manager for Autoliv, and I work at the Dachau site. And we provide this ECU, and my responsibility is to look into the standard development of this ECU. And I would like to hand over to Mr. Schramm, who is responsible for the software side.
Wolfgang Schramm, bin wie der Herr Reus.
My name is Wolfgang Schramm. I've been with Autoliv since 2016. And we, well, talked about these algorithms this morning. And in order to execute these algorithms, we need a safe hardware platform. And that's important for highly automated driving. You need safe computation of your algorithms. You need to provide for a safe startup, secure scheduling, the application, the calibration, and then the probability of producing faults cannot be precluded. So all this has got to be validated. So we need a safe synchronization of applications running in multiprocessor environment or multi-core environment. And you can also see the schematic on the right-hand side. So we've got a number of different electronic systems with separated safety and performance parts. They share one processor. And this is the technology that you're all familiar with. And for this purpose, we're offering, now from our experience in the passive area, we are offering a safe computation platform for algorithms, and freedom of interference has got to be safeguarded as well. Not only freedom of detection, but also freedom of protection, so that the fail-safe process does not have an effect on the ECU or affect the ECU, makes it fail or so, making sure that the vehicle stays somehow handleable. Then the safe execution, execution and scheduling. So we have software components, and they have been divided into runnables, different runnables, and the cores that you can see here. And as the title of the presentation says, we use ETAS, OES, and RTE. And then also the execution dependencies of the runnables amongst each other are accounted for. And at the same time, the core mapping, as you can see it on the right-hand side. Then the synchronization of the runnables. We have different sub-components that are integrated into your components. And we also have to provide for error and fault management of the individual software components. Then the safe computation platform, how do we synchronize on the hardware side, the performance hardware? Usually, they're not being classified as very safe. So in order to provide for a safe platform, we need hardware lockstep and software lockstep and other mechanisms, so as to make sure that a mistake or a fault in the computation can be detected. Then the multi-core systems, we need to make sure that we provide for a safe synchronization of the data. if there's synchronization on one core and the second application works on a different core. And then we also have variables that are used simultaneously and are interdependent. So in our standard project, the series project, that we've worked out a system which makes sure that the cores, as you can see in the small picture here, we have a software component with two runnables on the one core, and on the other core another software component with two runnables. So if they would run at the same time, how do we synchronize them? So there's a system which divides them into time slots. That's an architecture requirement that we have for our software application, software calibration. And then we have time slices that behave accordingly, and they can be scheduled safely so that they run appropriately and the system behaves deterministically. All the base software synchronizations are performed here along this intercore communication, this small time slot, which has been assigned to the runnable. So the base software is also synchronized, and so you can integrate your mechanisms so that even after every time slot, the software continues to run, because otherwise you need to restart your whole computation process.
Gut, also hört sich jetzt erstmal alles.
Well, this might sound on the part of software technology a bit complicated. How can I get all the cores together so safely as required by the ASIL level? We heard a presentation by Volvo, the ASIL on breaking it down to the component. This is exactly what we did. And then we have the requirement to bring it up to a specific ASIL level on our ECU. We offer the safe integration platform. We all work with the OEM, and all the function features above the RTE are integrated. And this has got to work in such a way that at the end of the day I can say, well, this has all been done safely, and then, of course, I have documentation, and also via the management, I can give this ECU a road release. So we've got an established cooperation model with OEMs. That's what we agree with our OEMs. And this happens like 15 times a year according to this similar structure. So the OEM will provide to us the data that we need in the form of an AUTOSAR, the AUTOSAR format. We get an ECU extract, an NCD update, and also the diagnostic specifications and memory specifications. These are our input data. Then from these AUTOSAR artifacts, we generate the RTE. Then the RTE is passed back to the OEM as headers. Then there are two processes that run in parallel at the OEM. They do all the function development above the RTE level, the overall architecture. On the Autoliv side, we move below the RTE layer. And, for example, for the NCD update, all the communication adaptations for the specific NCD update. Then we get the target software on the ECU. Then the binary that is built, which can be flashed to the ECU, either in a test operation or when there is a road release for the vehicle. Then it's done by our colleagues in France to do the final build. And once the initial software is complete, the libraries for the next iteration step go back to the OEM, and then we move into the verification phase, where on the OEM side we do vehicle validation, verification on the test tracks. Test drives are being done, and the colleagues in Romania, they do the test cases. Currently, we're talking about 3,000 test cases that are being performed in order to progressively secure the overall verification, so that we can give a recommendation to our management. I would like to hand back to Mr. Schramm for the last slide, where we're talking about our future vision. Well, the future development has already been covered by Mr. Fürst and more colleagues this morning. So we need a lot more computation power, and the algorithms or functions can run better on the current platforms, but we all assume that we will have much more complexity the more data we have, and the requirements will increase. So we need a safe platform for the future, and this is all part of our development portfolio, more processors than we have right now, and also in ADAS, a board with combined safety and performance part or smaller part, but also multi-processor parts for ASIL-D will be required. And another point, to provide more flexibility to you for security or for software updates or other possibilities. So for you to be more flexible, we offer virtualization solutions, and ETAS, the host for today, offers lots of possibilities, for example, on the hypervisor side, but also on the safety side or on the performance side, securing ASIL-D, ASIL-B, safety engineering, and also security, cybersecurity on the other hand.
Titel heute VRTE, alles, was sich Adaptive AUTOSAR.
Everything concerning Adaptive AUTOSAR, the future of the software, and for the computers, the vehicle computers we are going to install into our cars. The vehicle of today, as we know it, the typical premium class, about 100 ECUs and different actuators and strategic technological drivers, and this makes it more complex to control the cars. The autonomous driving with the data exchange, the quick integration of new software packages, features, and the vehicle should be updated all the time. Technological core functions distributed over various ECU, ASIL functions, and service functions, highly complex, and only few know that in the software complexity, we are with about 100 million lines of code, leaders in handling of complex software systems compared to other systems like Android, like an airplane, or particle accelerators. And in vehicles, the complexity increases all the time. What we are not showing here are all the data that we will transfer to the back end for processing, and this would multiply it by many factors. Means that we are going to change. We have to change something in the vehicle architecture, and this shows the heterogeneous architecture in zones with a lot of different ECUs. And with the increased amount of software and software modules, in the future we need centralization. We consider centralization not in the distant future, but we see a progressive development step by step of architecture to a domain mastering, which we see in 2019, 2020, and then more domain-controlled architecture by 2030, with more transfer to the cloud and back-end, and then a very strong cloud which hosts a lot of data functions and connected, automated, electrified. These are, of course, the main functions, and of course the expectation of the ultimate user. And we are going to do this step by step, this centralization. We are going to work with legacy share in the OEMs, from the OEMs, but it'll come.
Wir sehen schon 2019 eine Zusammenführung der
we see that there is a merging of the processors into a domain or into a centralized domain architecture with a strong lead processor. We are working on 3 levels, basically. The intelligent sensors. These are real-time requirements, the control units with the connectivity, intelligent activity, intelligent actuators. Then we have the central ECUs, which we call vehicle computers, of which in the current architecture we see between 4 to 6 such vehicle computers, which are characterized by the following. The central processors are standardized high-performance ECUs. We have the co-controllers, micro-based systems. They are connected very much. That means they exchange data. They take up the data from sensors, process them, and are connected with the backend, meaning they produce data for the backend, they receive updates, they get functional updates, and on the right-hand side, the structure of the vehicle computers in building blocks, starting with the hardware. It says here that the hardware will have a shorter life cycle in the future, which is due to the technologies. We are driven by the memories. Then the middle layer, the VRTE, which is the vehicle runtime environment, which we, as a basic operating system, have as an abstraction for the hardware. Then the security issue, and this coupled downward to the hardware, but also to the app domain, and the visible interface for the end user. That middleware will go to end user because applications will increasingly be developed and interface also to the data service provider in the future, because the data service providers are here also using and servicing this interface.
In Zukunft sehen wir 2 Typen von Vehikelcomputern. Einmal die Performance.
And here we see 2 categories of VCs. These are the classical IVI systems and a domain system, very much calibration driven, a lot of data flow, neuronal networks to service. But there are the other vehicle computers, the integrating one, not so much outlined to performance, but to flexibility. That means a lot of domains on the ECU, a lot of suppliers to the ECU, and very flexible as far as the update is concerned, but secure. Both families will exist. Both will be characterized by different platforms, will be available in the market, but with one common technology, and that is the software middle layer, the VRTE, based on AUTOSAR. And this is where we see 2 processes, because the security demands for both are the same.
Hier dargestellt, wie wir intern ECUs entwickeln, aber
this is how we internally develop ECUs, but also we have different OEM customers. They all use one platform by domain, and the same we have at the vehicle level. Per domain, we have different platforms, and the cross exchange, the synchronizing, is basically impossible. And aside from this status, there is another issue. We are all deeply embedded nowadays, meaning that we can functional safety of the C languages, that's where we are at home. But for computers, we will have to do more. We will have to have a different in the operating system. We will we will have to learn new technologies. And from the cloud computing, we are going to use technologies, and from the server technologies, where our data will be hosted, where we get the update from, and from the mobile world, all the networks that need to be supported to the operating system. So it's a different field, and As I said, 2019, we will bring the first systems to the market.
Das sind alles Dinge, die wir in Zukunft.
These are things which we will have to comply with in the future in order to be successful in the VCs with the OEMs and to follow the update concept and to security issue, tooling, new function design, and relocation of hardware, not enough storage capacity. All this is something that by way of new technologies, abstraction, multi-domain approach, standardization, these things that are driven through the consortium and links, for example, helping us with the virtualization. These are things that we are working on, and they will take shape next year, meaning that next year we are going to have as far as the maturity of the AUTOSAR standard is concerned, we are going to have a major level and the security requirements to such a system. How do we deal with it as Bosch? We have used the AUTOSAR standard for ourselves and have expanded it, adaptive AUTOSAR, to complex ECUs, and we have broken it down to 5 levels, which from hardware to vehicle-specific platform service develop. And we have taken the AUTOSAR function and our special functionality and software modules, clustered them. I have put down for you here what we know from the classical AUTOSAR. The layer structure is comparable, but additional layers are added. Or with the multi-domain approach, the functionality of the layers becomes more complex. What does it look like when we go into series? Here, more or less, the superset. We have the microcontroller, the microprocessor. On the left-hand side, the AUTOSAR classic environment, and on the other one, the legacy with the AUTOSAR and the highly security and safety relevant. And then we have adaptive cells, and further to the right we have special cells which are more driven from infotainment or specific vehicle computers where these cells are also implemented. The superset, that is the realm of possibilities of what should be possible, could be possible, but which for the first vehicle computers 2019 is foreseen, is this setup. From the left we start with the microcontroller with a classical AUTOSAR. That is the microcontroller controlling the system so that the ASIL requirements are implemented. On the right-hand side, we have another AUTOSAR classic cell, which is already planted onto a hypervisor, where we have the monolithic software functions that are not exposed to update, well-defined safety. And then we have the adaptive cells shown here with 2 adaptive AUTOSAR domains on the hypervisor and a Linux cell that we also see here. And with this setup, we currently approach the development with the AUTOSAR Adaptive Consortium and drive the internal platform for the integrating processors and the performance ECUs. And to sum up, I would like to say the vehicle computer is not something for the future. It will be reality by 2019. And we are going to have processes with a high level of standardization, which are living with outside communication. Adaptive AUTOSAR is the technology we are using in order to establish our VRTE as a standardized core for the vehicle computers. The VRT middleware is the expansion of the standard as it exists today on multi-domain and the whole vehicle. It has to work in the vehicle, and this is why we are a member of the Adaptive Consortium, and with a classic AUTOSAR VRTE will be available. Nigel, does it fit? And next year, ETAS with the tooling. and we would be happy if many would follow us in establishing the standard.
Und Sie sind aber dann auch in der Lage, Software, die beispielsweise
Okay, but software coming through a smartphone or apps that can also run on this platform.
Wie eben schon angedeutet, wenn
Well, as I said before, if we don't succeed to make the systems updatable, we talked about security and communication control and shared memory. At the end of the day, we don't care whether the app comes from the smartware or from a server, but the system must work safely, and the technology, we have shown them the technologies we need for that.
Und das Thema heute ist vielleicht für den
And my topic today, maybe it's a bit new for you, microservices architecture. So how can we use this in connected car between cloud computing technologies and embedded?
Also bevor wir einsteigen, vielleicht ein paar Worte zu Microservices.
Let me just fill you in on microservices in general. It's the technology trend in cloud computing technologies. Cloud computing, well, they really reach into all industries, and they actually revolutionize the way technology is integrated into different IoT environments. So that's really, really interesting, but I'd like to show you what it means for connected services and what we're already doing in this field.
Also heute, so wie der Kollege gesagt
Now
hat,
today, as a colleague has already said, today we are highly connected and embedded. Everything is totally dependable in the vehicle. So hardwired interfaces between the applications, for example, in infotainment systems. We have architecture which is organized along Conway's law, which means that the architecture of a technical system always reflects the way it is organized. This can be good, but it can also be not so good in some cases, and I'm going to show you what this means. Then we've got our development model, the V model, like a waterfall cascaded model, and this is simply what the world looks like today. What we would wish for now, every time a customer comes and says, well, infotainment systems, they want a new function in the car available. So what they really want is to make it function the next day. And these new functions have to be implemented in the form of applications. And these applications are supposed to be created ad hoc according to the wishes of management or the customer. And also we want everything to work continually. So we would need some kind of approach to continuous integration, continuous deployment, CI/CD, that's what it's called in the abbreviated form. So the thing is that if you want it, or your customer wants it, or management wants it, you want to be able to implement it more or less overnight.
Also heute haben wir im Prinzip folgenden Aufbau. Wir haben die UI.
We've got the following setup. We've got the UI. In our case, these are Qt. So applications stacks such as remote UI for audio and media. Then we have the basic software layers where you've got the interfaces. Then we also have an operating system. So it just depends on where you put it, and you've got a certain hardware. And the main issue is not even software engineering or software development. You know, the main issue comes if you want to integrate everything. It's very difficult to integrate new software. Why is this so? I'm going to try to give you an example. If you open or close the doors, you might need an app to do that. So you want a message on your head unit so that telling you that this has happened, and you want to do that, to have that on the cloud as well. So if you have a hardwired technology architecture, it is enormously difficult to get this done across the whole number and mass of features. So what we'd like to achieve is some kind of decoupling of the individual services, decoupling in such a way that, again, afterwards, you can integrate them seamlessly again. But I'm going to cover that later, once again in my presentation. But this is, you know, the statement, if it is already difficult with the door, and then we've got IoT devices in our car, we want to integrate new functions into the car. How can this be done? What is a good integration platform? And how is it supposed to work across the whole number of ECUs that would be required? And actually, there's a formula, n times n minus n divided by 2. These are the number of possibilities that I have to include new services. So it becomes rather clear that the integration of new services or functions is enormously complex. It's really, really difficult to master that. So the question becomes, is this the right approach? And what would be the steps to actually change this? That's a bit technical now. I try to explain what this means. The basic idea of a microservice is, now today we've got all these monoliths, for example, in the infotainment system, where all the functions happen in this big piece of software. So this piece of software has all these functions. Now, if you want to integrate something into that, then you've got to do all this within this monolith. The new paradigm now says that an application consists of all these small microservices, and these microservices are decoupled in such a way that I can replace them individually. It's an idea that comes from large mega websites. These large mega websites have highly sensitive requirements regarding fail, safety, timing, and so on. So there are really these microservices that you can exchange, replace on the fly, and customers won't even notice it. So instead of building monoliths, we're building these small microservices, and aggregating these microservices gives us the larger application. If we take this seriously, then it will have quite positive impacts. Because you can now take lots of parallel development teams to build these microservices. And the question then is, how can you get with such a microservice into a system such as infotainment? You can see the tool chain as described here. So you would end up with a kind of containerization of these services in the head unit. Maybe let's go one slide back. Now, if I have a function, if I want to update such a function such as navigation, the GPS, it would consist of 10, 20 microservices, and I would then have a container in which the application is running. I would only supply the 2 or 3 changes. So I wouldn't change the entire monolith, but only these 2 or 3 small microservices. So that makes me much faster in updating this function, because I can do it more or less every day if I want. So the question is, where do you start? Where do you begin? Well, usually with the system. You try it with a system where it doesn't matter so much. Let's say an infotainment system that is a system that transports information. So if there is a service there that needs to be replaced because it's somehow faulty, I can do that the next day, and it will not have an impact on safety. Maybe it's a bit annoying for customers, but you can do it. Internally, we had lots of discussions with quality assurance. Because what this is, it is a paradigm change. If you have a V model, you're targeting some kind of release, and you want certain software functions available on a day X, or, on a specific date. You would then have to abandon this approach a bit. If you have continuous updates, this will bring you some quality enhancement. So in the field, you don't want the car rolling off the production line and then it's ready and finished. So it will be different, or it's a new approach. But then it becomes interesting to explore how we can take this further, because this is only the first step. Now let's take a look at this slide. What's important? What do we need in order to be able to do that? What we're doing at the moment is we are trying to containerize parts of the infotainment system. We have a phone application, and we try to put it into one container. And we're doing that not only to be able to update the function, but there will be a point in time where this entire head unit has to be implemented in a car, quality assured. So the applications that have been built in the head unit have to be protected from each other. If you do bug fixing in the head unit and you want to get your GPS application stable, usually what happens, I think, in the automotive industry, whenever there's a function update, this would potentially have an impact on other areas, other applications in your head unit. Well, if you have container management, this means that you can do change groups. If you know Linux, you know what this is about. So you do not only isolate applications from each other, but you also isolate resources. So you can allocate CPU storage, CPU memory to one application, such as the main application, such as GPS, for example. So in terms of quality assurance, the consequence is that if you can stabilize these containers step by step, you can be much faster when you have to do bug fixing for the whole system. So this is something that we're trying to tackle at Daimler. And the world is becoming more and more complex, as you can see here, all the cloud systems. And to a limited extent, that's got to do with these microservices, because they are also part of this cloud to some extent. The car will be connected or it will not be connected. It doesn't always have cloud services available, but that's not a contradiction, because microservices can also be built within embedded systems. The main difference between microservices in an embedded system and microservices in a cloud system is that usually you wouldn't have any dedicated databases that are allocated in an infotainment system or in a head unit. So you wouldn't end up with 100 instances of MySQL databases, but you have a service which looks like a microservice. So that's just the slight limitation. Now today, many technology providers are experimenting whether we can build central microservices. Amazon, Microsoft, Cisco is trying to build edge microservices in order to centrally control how such a service kicks in an embedded system and when it comes from the cloud, so that it really, in the end, doesn't matter where it comes from for the customer. So you need a good isolation from the APIs. I'm not referring to middleware systems, but I'm referring to interfaces which are built in such a way that you can consolidate them from the system. Middleware is not the same as APIs. Middleware systems are usually messaging bus methods which you use, for example, for asynchronous processes. But actually, 80–90% you can provide services via the API world, which is something a bit different. Now, if this were to work properly, and actually we have a prototype that is running end-to-end, but there are some requirements that need to be met. So that's a developer slide. What do you need? So that cloud services plus the IOI component, so also the embedded service plus the IOI service and the embedded service can be deployed together. Now, why do we have that? Well, it's a matter of scalability for the software teams. In this case, it's a cloud platform. Do they have to access the cloud platform to develop it there and then bring it to the head unit? So first step, we need some kind of code, central code repository where we store all the code from the cloud services, but also from the infotainment services. Then you would build these different services. So then you can have several built environments. So you can have one team building the cloud service, the second team the cloud service, and the third team the UI service. And then actually you can do component integration. Now this looks similar to an embedded environment, but it is something totally different. Especially when it comes to microservices, there is tooling where you can test these services in dependency of each other, or you can provide the head unit in a virtualized form. Then you've got end-to-end integration tests, and for such a distribution repository, you can deploy these software packages for an end-to-end environment. So this sounds interesting. We just have to make sure that it actually works. So here we've got different application or use cases. One use case is the question of, if you have test fleets for specific vehicles, how can we add individualized services and make sure that you don't have to build a new branch, but that you can provide new services in the production code? Now that sounds a bit strange, I know. So let's say I have a tested sub-function and put it in production. There's a technology around that's called feature toggles. Have you heard of feature toggles? Now, feature toggle is the idea to plug in code parts and to be able to plug them in and plug them out again. So the production code and those who use additional features and the people who are on the production side, they don't even notice it. So that's state of the art, the way software is built today. So if we had that, you can think about different other topics also for development. The development teams can do things in parallel, because today we have the problem that the functions are interdependent in such a way that integration is so difficult. But by decoupling all these microservices or mini-services, it becomes much easier. Because there might still be an error or a bug, but the function development or bug fixing can be rolled back in the same production code rather easily by just deploying this small service instead of the entire big monolith. So that's the advantage, that's a benefit for the development teams. The security, of course, is a big issue. I also have car IT security as one of the topics that I'm responsible for. And of course, you can't wait if you have a security issue for the next release. You've got to fix it immediately. You've got to fix it tomorrow. Otherwise, you've got a brand problem or a containment problem. So this is actually the strongest driver behind making sure that software updates a piece of software which is still monolithic and be able to just plug it in. And I think this is the second trend next to virtualization. I always say, as long as these are information services, you can go straight for container management systems. And if there are domain controllers, domain computers, then I would think you've got to do the intermediate step on the central vehicle platform. Well, Docker or container management systems can be used within a VM system. So that's not a contradiction. Both ways are justified to get to a new architecture in the car.